Dear audience, I thank you for the invitation today to present my research work entitled Improvement of Redundant Manipulator Mechanism Performances Using Linear Parameter Varying Model Approach. Elaborate in the research laboratory in automatic control Lara of UNIT in co-supervising with Laboratory Advanced Control Systems of UPC, authored by me, Sameh ZRIBI, Gillian Kneni, and Vicence Puig. The outline of our presentation is composed of 5 parts. After the introduction, the second part presents the description of the dynamic modeling of a redundant manipulator mechanism, where the mechanical structure of the rigid flexible robot and its assumptions are detailed, then the dynamic model is calculated. In the third part, I will present the simplification of the dynamic model, where the linearization and linear parameter varying approaches are described. Then the simulation results of our system will be discussed, and finishing with conclusion and future works. The studied system described by the redundant manipulator robot is a combination of a rigid structure and a flexible structure mounted in series. These rigid flexible robots are characterized by higher velocity and lighter weight. These characteristics allow to optimize not only the time but also the energy consumption to facilitate the object manipulation and to improve the safety. However, it causes negative effects such as important vibration and wrong positional accuracy. Mathematically, the dynamic model of a redundant structure is nonlinear and complex. As a result, its control is very difficult mission to achieve. To remedy these difficulties and in order to ensure higher performances of the rigid flexible mechanism, 3 improvements can be taken into consideration, which are the development of the trajectory planning, the improvement of the dynamic model, the synthesis of an adequate control. In this research work, we will focus on improving the performances of the redundant manipulator mechanism by simplifying its dynamic model. As shown in Figure 1, the considered case study is composed of a rigid arm and a flexible and effector, where a mass load denoted by M is fixed on its free extremity. These bodies are interconnected using pivotal joints, where its parameters are described as follows. In order to perform these rotary connections, 2 DC motors are placed directly on the links. The inputs of this robot are described by the torque values provided by the DC motors, and its outputs are described by the value of its joint angles. So, the following dynamic modeling assumptions will be considered. First, the robot's motion is assumed to be in the vertical plane. Then, for the flexible arm, the shear strength, the rotational inertia, and the effect of the axial force are ignored. In order to guarantee its vibration in the horizontal direction, The flexible arm is characterized by a depth assumed to be smaller than its length. Moreover, its length is considered to be constant to avoid the problems and difficulties resulting from the variability of the length of the flexible arm. Excuse me, one moment. I will do the LPV approach. Okay. This approach is not an approximation based on an order reduction, but a rewriting of the system in a form having a structure endowed with particle properties. An LPV system is defined as a finite dimensional LTV abbreviation of a linear time varying system whose state space matrices are fixed function of variable parameters as shown in equation 7. Each variable parameter and its derivative vary over known extremity values as follows. The admissible set of bounded convexes is generated by this construction, which are described by equation 8 and 9, and the LPV representation is not unique. It depends on the choice of variable parameter vector. In our case, the reduced schedule functions are given by equations 10, 11, and 12. So, after computing the dynamic model of rigid flexible manipulator mechanism, the torque is applied to each joint for several motion profiles. The numerical value of the parameters of the rigid flexible mechanisms are summarized and given in table 1. Let us set the numerical values of the PED controller parameters summarized in table 2. Concerning the LPV model boundary, its limits along generating the admissible set are defined as follows. The simulation are performed using PED control and initializes the system parameter as seen in the two preview tables. Figure 2 presents the system responses of torque applied to the second joint for trapezoidal profile. This profile ensures a discontinuous torque that varies between 25 and minus 30 Newton meter. For this motion profile as an input, we note that besides the flexibility problems, the discontinuity problem of the torque of this input degrades the system performance. For smooth motion profiles described by fifth polynomial motion profile, the simulation result shows that in comparison with the nonlinear model, the linearized model follows better the reference signal. However, the LPV model follows better the reference signal with low variation in comparison with the two other models. As shown in figure 4, the tracking error presents some peaks, especially for the trapezoidal motion profile. It means the trapezoidal profile. However, for the smoothest profile described by the hyperbolic profile, the tracking error are neglected in comparison with other inputs. It's clear that for several motion profiles, the magnitude of tracking error caused by the LPV model is smaller than that of linearized model. Furthermore, at t equal 0.23 second and at t equal 0.43 second, the tracking errors for the two modeling approaches present two peaks for trapezoidal motion profiles. It indicates that the studied system is sensitive to the torque discontinuity and especially for the trapezoidal motion profile independent to the used modeling approaches. In contrast to hyperbolic motion profile, we can observe that the tracking error for the hyperbolic profile is characterized by slow moving with low amplitude compared to that obtained for the two other profiles. It was the main purpose of this paper to draw attention to the LPV modeling method and its robustness against the linearized modeling method in the presence of motion profile characterized by discontinuous torques. In this research work, the dynamic model of the rigid flexible manipulator robot is detailed using Euler-Lagrange formulation and the finite element method. The improvement of the dynamic model is developed using the linearization and the LPV approaches. Via MATLAB Simulink software, the robustness of and the effectiveness of the approaches of simplification are simulated using motion profiles characterized by its discontinuities in acceleration. In the future works, we will focus on improving robust control to be able to the LPV model of the studied system, then evaluating its performances using several motion profiles. Thank you for your attention. If you have any questions, don't hesitate to contact me via my mail.